So let's talk a little bit more about sound and get some notes down about it. So I said before that sound is a longitudinal mechanical wave, and just want to remind you what that means, and that's what we have here. I have this um, barrier that's moving back and forth, and if you remember the other word for a longitudinal wave, it was a compression wave. And that's super important because it's really descriptive of what's going on here. You can see that this is supposed to simulate air. So if you think about a random scattering of air particles, what's happening here is this diaphragm is moving back and forth, and it is compressing the air in front of it, and then it moves back, and it causes this gap between the air. And then you can see the pattern of compression traveling down. And that's pretty well shown down here. It shows any given particle, remember, is going to stay still and vibrate back and forth, and that the energy pattern travels through out to something. And so this is what a sound wave looks like. And so let's talk about what the names of these things are. Whereas we had crests and troughs in transverse wave, what we have here on a longitudinal wave are compressions, which are the regions of more compressed matter, which are like the crests. And then we have the regions of low compression here, which are actually called rarefactions. And I'll spell that for you later so you can see it, but that's less compressed air. So that's really what's going on here. And a wavelength would be from maximum compression to maximum compression, or minimum compression to minimum compression, and so on and so forth. The amplitude of this wave, I don't know why I just did bunny ears because it's just the amplitude, is related to the difference in pressure between the high pressure and the low pressure region. But I'll show that in a different dimension in a minute. So compressions, rarefactions. Those are our two new vocabulary words there. I just want to show this in a different way. This is actually showing what's happening with a tuning fork. So the tines of the tuning fork are vibrating back and forth, and what this is trying to show you is as the tine of the tuning fork moves to the right, what it does is it compresses the air in front of it. In the same way that if you're standing on a subway platform or the train platform and the train is coming to you, you feel that whoosh of air as the train arrives, because what it's literally doing is compressing and stacking up the air molecules in front of the train. And then when the train leaves, that feeling where it feels like the air is rushing in behind the train, that's because the train was occupying that volume, and then it leaves that volume, leaving behind what's known as a partial vacuum, or a low pressure region, and that's that rarefaction that we talked about. And so that's what this is trying to show. Just to demonstrate, and here's your spelling of things. You have compressions, rarefactions, but you see the way this is like compressed and then stretched out, compressed. It's generally not that sudden. In fact, we can graph a transverse wave so it looks like a longitudinal wave, so it looks like a transverse wave, because what we can look at is the air pressure, right? And air pressure goes to a maximum at the compression and then goes to a minimum at the rarefaction. And it actually is kind of a sine wave in between. So it's not just like compression, rarefaction, compression, rarefaction. It is a continuous graph. And so pressure versus time, or pressure versus position graphs, are the way that we actually represent sound waves. So the difference from atmospheric pressure, this should not say 0, by the way. This should say 1 atm, or atmospheric pressure. So from atmospheric pressure up to the maximum pressure, that's the amplitude of the sound wave. Okay? And so that is the structure of a sound wave, how we would measure wavelength, how we would measure amplitude. But let's just talk about words then that we use to describe sound wave. So I said this in the past video there. Let me go up there to the front. Rather than talking about the frequency of a sound wave, we talk about the pitch of the sound wave. Now, there are some other words that are used when talking about frequency. You might have heard the word tone used before, right? And pitch and tone both do mean frequency, but they mean something slightly different. So pitch literally is just How many times does the air particle vibrate back and forth, right? That's the most basic. But tone has some other additional meaning to it, which I want to demonstrate now. So let's take a listen. Online tone generator. Ready? If you have your sound turned up, you might want to turn it down because this is annoying. So that is a 440 hertz tone. You may recognize that sound because that's our bell, right? Our bell plays at 440 hertz. I can change that a little bit. I change that a lot, right? Higher pitches, lower pitches. And this is the pitch increasing. Now, as I do that, you might notice that even though I am not changing the volume of the sound, that some of these sounds sound louder to you than others. We'll get back to that in a different thing, because volume is going to be different. Oh, that's unfortunate. 6666. Whoops. Volume, right? Like, actually, that should be louder than that is for very specific reasons, and we'll talk about those in a couple of minutes. But I want to talk about the difference between pitch and tone now. And so the easiest way to do that is listen to this. This is a guy playing trumpet.
I want to be able to hit a clear C.
So that's in music a C. I'm going to play a C on this tone generator, and that should be, actually, let me just come over here and we'll pick C. So that's C. And that's C. And they don't sound the same, even though that bop, that's a C as well, right? All of those have the same frequency, the same pitch, but they have different tone, right? And that's what we're talking about here, is the difference between those sounds. Let's actually, where'd you go? Sorry. Those are for later. Okay, I lost one of my things that I wanted to show you. So let's go back here and I'll just call it back up on the screen. Okay. Sorry about this, folks. There it is. All right, and so we can hear this in a different way as well. So once again, we have the tuning fork. Right? And playing the same pitch, but now the clarinet. Okay? Playing the same pitch, but now the flute. Let me play that again. Playing the same pitch, but now the trombone. Well, abbreviated there. Playing the same pitch, but now the violin. Playing the same pitch, but now someone singing. All right, and so the difference between pitch and tone can be figured out by looking at their pressure waves. And so what I've done here is I have a graph that shows the pressure wave of a perfect sine wave. This is actually what you get from a tuning fork. And it's actually what you get also when a flute is played correctly. You'll notice that this is perfect, that sine wave. A guitar, notice here, the pattern repeats just as often, i.e. it's just as frequent, meaning the pitch is the same, but the tone would be different because of the shape of the sine wave. And a piano, once again, the same frequency, but a different structure of wave. And so that's the difference between pitch and tone. Pitch is just merely the frequency. But tone is frequency plus how pure the sound sounds, meaning how close is the pressure wave for the sound to a perfect sine curve, right? So you may, if you're a singer or you play an instrument, you might have your music teachers talk about, ooh, that person has good tone, that person has good pitch, and those are different things. Someone who's good pitch can match the correct frequency, but someone who has good tone, it also just sounds clearer. I personally, as a singer, have terrible tone, a very warbly sounding voice, but that's for reasons. But anyway, pitch versus tone. Both mean frequency, but tone means something a little bit different. There's another word that you might know that's also called timbre, but spelled timbre. We're not really going to get into timbre, but timbre is another thing that talks about the quality of the sound, but that's more about how you attack the sound. So like, right? And how you come away from the sound rather than other things. And that has to do with how warm the sound sounds or how other things deal with quality of sound. But that's not as scientific a term. So we're not going to talk about it. Whereas pitch and tone have a little bit more of a scientific basis to them. So now, other things. We generally don't say amplitude of sound, right? What do you say? Well, two words here that are related to amplitude. Now we know that the amplitude here is related to how far the pressure wave goes from 1 ATM. That's the amplitude of the sound wave. But what are some words that you go with that? Hopefully you know the word volume and you know the word loudness. Volume is not the same thing as loudness. Volume is a much more scientific term and it's measurable. But loudness is about the human perception of that sound. And that has a lot of parallels here to frequency or the pitch and tone, because pitch is purely mathematical. It's how often the pattern repeats. Tone, because we're talking about how pure, there's a quality sounding to it. That's something about how we like it or don't like it is related to nice tone versus not nice tone. So there's a little bit of human impression in those terms. But what is volume then? It is related to the amplitude, but really volume is more properly called sound intensity level. Okay? And sound intensity level is based on the intensity of the wave, not the amplitude of the wave. And so we'll talk about intensity of a sound wave a little bit later. But you may know a scale that measures sound intensity level, and that is the decibel scale. And once again, we'll talk about the decibel scale a little bit later. Loudness, though, is the human perception of it. Two things can have the same volume, but one might sound louder to us than others. And that's sort of weird. And there's a reason for that. And it has to do with something that we've talked about before. And a word that we've talked about before was resonance. Who remembers what resonance was? Well, hopefully you remember that resonance was a situation of maximal efficiency of energy transfer. There are just certain systems where they transfer energy to and from more efficiently. And so things would sound louder if you have that situation of maximally efficient energy transfer. So I think I'm going to try and demonstrate that now. So notice I have here an empty vase, okay? And I have a pitcher of water, and I have my tuning fork here, right? If I put the tuning fork over, hopefully you can hear that. No big deal. But watch what happens when I start pouring some water in. Okay, I gotta get this going here. Do you hear how much louder that is? than it was before, right? This is just the tuning fork. I put it over this. There's something about this column length of air that resonates with this frequency of tuning fork, right? So since these two things like to vibrate at the same frequencies, i.e. the structure of their standing waves are very similar, they efficiently transfer energy to and from things. And that motion is something that is called vibration in sympathy, right? And this is when you have two objects whose natural frequencies or modes of vibration match. When that happens, what happens is that one object vibrating causes the other to vibrate, thereby reinforcing the sound. Okay, and so that vibration and sympathy is an important thing. Going back to that online tone generator, which is annoying, but there it is, right? Notice here, I'm not adjusting the volume, which is a scientific measure about how much energy your speakers are putting out. Something usually somewhere around here is going to sound louder to you than that does. And then something around here usually as well than that. And somewhere around here. And what it is that your ears have certain natural modes of hearing. And so when those pitches are played, you hear them as louder because there's a more efficient energy transfer to your ears than what you would normally have. And that's why some sounds sound louder than others. So loudness is not only based on the amplitude or volume of the wave, but it's also based on certain frequencies will sound louder than others. So it is very much based in human perception. And not everyone is going to have the exact same frequencies at which they receive those waves more efficiently, but we're on average all about the same, which is why we should have heard certain of those sounds as louder than others together. So those are some words that get used with sound. A couple more that I want to talk about, and then we will call it a day here. I want to talk about the concept of an octave. So an octave are two frequencies in a 2-to-1 ratio. That's all they are. So for those of you who like music, you may know concert A as a note, 440 hertz. This is when you hear orchestras warming up. This is the note that they're playing, right? So 440 hertz. An octave of concert A would therefore be 880 hertz, right? And that's how that goes. And an octave above that would be 1760 hertz. And an octave above that, and so on and so forth. An octave below 440 hertz is 220 hertz. So it's just a way of talking about that. And that's the way that our music system is set up, is based on the concept of octaves and ratios. But we're not going to get too much into all of that. The last thing in terms of basics of sound we have to talk about is the speed of sound. So what is the number one thing that's going to determine the speed of sound? Right, the medium of transport. Okay, so generally the medium of transport is air, right? And so here's the thing. What is it that determines the speed of sound in air then? Well, the main thing, there's a whole bunch of things that could affect it. But the main thing that affects the speed of sound in air is the temperature. Now, I will say that there are other things that affect the speed of sound in air, like local density of the air will matter, the local pressure, humidity, all of these things actually matter. But the one that has the most impact is temperature. And we've discovered that the speed of sound in air, so V of sound in air is 331 meters per second plus 0.6 Celsius meters per second per degree Celsius. Hard to write that on this format. Meters per second per degree Celsius times the temperature in Celsius, right? So on a 0 degree day, the speed of sound in air is 331. When it's warmer, the speed of sound is faster. When it's colder, the speed of sound is slower, right? Some other facts about the speed of sound. Speed of sound in water, what do you think? Higher or lower? The actual answer here, the speed of sound in water is about 1,500 meters per second. It's much faster. And people are thinking to themselves, hold on a second, but the sound sounds all garbled in water. Why is the speed of sound faster? Well, the garbled sound has nothing to do with how fast the sound's going, it has everything to do with that pressure wave, right? Think of sounds that are easy to hear underwater. Those are like whale sounds, right? Like everyone make their favorite whale sound. And then so on and so forth, right? The pressure waves for those are very regular and very even. The pressure wave for my speech is very erratic, and therefore it requires lots of changes in motion, and therefore it doesn't transport well. Whereas with those beautiful, like long, low sounds, you're able to do them fairly clearly because you're not trying to change the way the particles are vibrating all that often. And that's why we can't really do human speech underwater, but you could do whale speech underwater. And it has to do with how we're trying to wiggle those water molecules in order to transport it, but much faster. Another thing that commonly carries sound is steel. Like think about the two cans on the end of a steel wire. If you've ever made a little telephone, speed of sound in steel is about 5,000 meters per second. So hopefully what you can see is the denser the object is, actually, the faster it conveys sound. And that's because of the compression, right? We're trying to actually use the physical interaction between the molecules in order to transport the energy down. So that should make sense then, that when the molecules are joined together in a more formal way and in a rigorous structure, that we can transport that energy faster. Now, that doesn't mean that we can transport the message easier. It just means that something about the speed at which it goes. So there we go. We've discussed the structure of a sound wave. We have words that describe all the things that we use to describe water waves and mechanical waves, and we're going to use that vocabulary in order to do quite a number of things this week.